Okay, sir.
See. In the first unit, did you solve some SAQs? You please look into the first unit, SAQ 1. Show by an example that the intersection of a countable collection of open sets need not be open. I will show you.
So page number, sir?
This is World Book 3, SAQ 1 in first unit. I'll write down. Show by an example. Okay, this is SAQ 1 in first unit. Show by an example that the intersection of countable collection of open sets. Countable collection of open sets need not be open. Could you locate? Need not be open. Okay. Hello? Could you look at that? SAQ 1, Unit 1. Show by an example that the intersection of countable collection of open sets need not be open. Could you look at that? Okay, no problem. I'll just explain. This will help you, in various cases. Okay. See, what he is saying. Did Ramlinga teach this SAQ? Did he solve this SAQ? Hello? Hello?
No, sir, no.
Okay. What here we are asked to show by an example that the intersection of countable collection of 1 minute. Cheppu Saranya. Saranya Cheppu. We have to give an example of a countable collection of open sets that need not be open. Look at this. On the number line, let us take a point. Okay, small a. This is the real line, right? This is a real line, and small a is a real number. Small a is a real number. Okay, so. Sorry, there was a student. Okay. So on the number line, take a real number A. Hello? 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 Are you there? Is anybody there?
Yes, sir.
Okay. So some student came and okay. So on the number line, I am taking a real number. Around real number, I will take a countable collection. How? See, I'll take this collection a minus 1 by n and a plus 1 by n. Okay, and I let n be any natural number. N is 1, 2, 3, and so on. What happens? If n is 1, what happens? This is a minus 1, a plus 1, right? A minus 1 may be somewhere here, a minus 1, and this is, this may be a plus 1, okay? And then I'll take n equal to 2. Then what happens? A minus half, a plus half, okay? This is for n equal to 2. For n equal to 1, I get a minus 1 by 1. That is 1, comma, a plus 1 by 1, okay? Right? So how to, let us mark this. A minus half will be somewhere here. From a, you have to subtract half. This is a minus half, right? And then this is a plus half, okay? So I am taking open intervals. So let me give different colors. Okay, from here to here, it is red color. Okay, this is red color interval. Is this is a minus 1 to, this is a minus 1 to a plus 1. Okay, and then yeah. Up to here is a minus 1 to a plus 1, and then I'll give blue color to a minus half to a plus half. Okay, this is the second interval. Okay, for n equal to 2 you get this. For n equal to 1 you get this. What is the intersection of these two? No, up to here it comes. The red one comes up to 1, up to this a plus 1. I'm sorry. Okay, this is a minus 1, a plus 1. So this is right. On the number line you have to take. Here you have to take actually. Okay, this is a minus 1 to a plus 1. Just to make you understand, I'm drawing it above the interval, but it is on the number line. Okay, so what is the intersection of this blue one? What is where is blue one? Blue one is from here to here, from here to here. Okay, this is blue one. This is a minus half to a plus half. What is the intersection of these two intervals? Hello, can you tell me? What is the intersection of these two intervals? Right, the intersection of these two intervals is the lower, smaller one. This small interval is contained in the larger interval. So the intersection of these two is what? The smaller interval. And if you take n equal to 3, what happens? This is a minus 1/3 and a plus 1/3. Right? So and 1/3 is less than half. So a minus 1/3 will be somewhere. A plus 1/3 will be somewhere here. A plus 1/3. A plus 1/3. And a minus 1/3 will be greater than a minus half. This is a minus 1/3. Okay. So if you look at this interval, right? Let us use different color. Maybe this one. Right. Right. This is a minus 1/3 to a plus 1/3. And this small interval is contained in this interval, this blue interval, and it is contained in red interval. This is stuff color. This is contained in blue interval, and blue interval is contained in red interval. So what is the intersection of these three intervals? It is the smallest. It is the smallest interval. It is this a minus 1/3 to a plus 1/3. So the intersection of these three is this. This interval is contained in this, and this is contained in this. Okay. So the intersection of all these three is the small one. So if you let your n go to infinity, you will be getting smaller and smaller intervals around a. What is the intersection of all of them? What is the intersection of all of them? Okay. So what is intersection a minus 1 by n, a plus 1 by n, as n varies from 1 to infinity? What is the intersection of all these? This becomes singleton a. Okay, you can show that this is singleton a. Each of these intervals will be containing small a. Each of these intervals, right? Each of these open intervals contains a small a. Therefore, this is contained in this, and right, and whichever interval you take, no other points of this interval, of any of these intervals, will be a point here. Okay, no other point of any of these intervals will be a point here. Right? Okay, you can show that. For example, no point, only A from this belongs to this, and no other point belongs to this. Okay, so no other point of this belongs to this. So so we can so the intersection of all these becomes this. And how many are these? These are countable. N equal to 1 to infinity. These are countable number of intervals, and these are open intervals. Each open interval is an open set. Okay, so this is an example of a countable collection of open sets whose intersection is singleton. This singleton is closed set. Singleton is closed set. On the number line, with the usual topology, singletons are closed sets. Okay, so this is an example of a countable collection of open sets whose intersection is closed. Okay, so this example often helps in various cases. You have to remember that. Okay, let me try this example. SAQ2. Okay, SAQ2, right. SAQ2. If F is the collection of all closed sets in R, if F is the collection of all closed sets in R, okay, prove that number one, F1 belongs to F. Let me take script F here. So this is script F. So F1 belongs to script F, comma, F2 belongs to script F, implies F1 union F2. F1 union F2 belongs to script F. Okay, number two, if F alpha belongs to delta, is a collection of sets in F, then the intersection F alpha belongs to lambda delta belongs to script F. Okay, before this one, yeah. Okay, how can you prove this? If F is a collection of all closed sets in R, prove that F1 belongs to F, F2 belongs to F, implies F1 union F2 belongs to F. Okay, right? And if F alpha is a collection of sets in F, then intersection of F alphas belongs to F. Why? This is because, yeah, if you take, say, F, what are script F? This is a collection of closed sets. So F1 is a closed set and F2 is a closed set. How about union? Union of finite number of closed sets is closed. How to prove this? How can we prove this? Proof. Right? Yeah. We want to, we can show that union of finite number of closed sets is closed. Here you have two closed sets. You can show that their union is closed. How to show a set is closed? You look at its complement. What is the complement of this? Can you tell me? Hello. What is complement of this? F1 complement. And then comes what? De Morgan's laws. What is De Morgan's law? Hello? 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 Is there anybody? Hello? Vijay?
తేజ ఉన్నామమ్మా?
Yes,
తేజ.
sir.
Okay.
Sarita is online.
Okay.
హెడ్ ఆఫ్ ది డిపార్ట్మెంట్ చెప్తున్నారు, మధ్య మధ్యలో ఒకసారి రెస్పాండ్ కండి. మీరు ఉన్నారా మ్యూట్ చేశారు తెలియదు కదా.
Okay.
Okay, sir.
So
Sir.
Yeah. Now,
Sir, which chapter, sir?
Ma?
Which chapter, sir?
Which page? This is. I have the old book. This is not the new one. Okay, I'm talking about this.
Okay, sir.
trying to explain this set you. If
Okay, sir.
F is a collection of all closed sets in R, prove that F1 belongs to F, F2 belongs to F, implies F1 union F2 belongs to F. Okay, and if F alpha belongs to delta is a collection of sets in F, then intersection F alpha belongs to F. Okay, here what is this? This is the property that script F is closed under unions. Okay, and what is this? This speaks about the closure of script F under arbitrary intersections. Okay, and we are taking two closure sets. Script F is a set of closure sets. Okay, so the F1 is closed and F2 is closed. We have to show that F1 union F2 is closed. How can we show? How to show two, right? Union of two sets is closed. You look at its complement. We want to show F1 union F2 is closed. Okay, our assumption is F1 is closed, F1, F2 are closed. These are two closure sets. Okay, by assumption, F1, F2 are closed. We are looking at their union. We want to show this is closed. So look at its complement. Look at the complement of this. What is the complement of this? What is the complement of union? If F1, it is F1 complement. What else comes here? By De Morgan's law. What else comes here? Can you tell me? This is this intersection F2 complement. Okay, by De Morgan's law. By De Morgan's law, this is F1 complement intersection F2 complement. Complement comes both of these, and then this becomes union becomes intersection. Now F1 is closed, therefore this is an open set, and F2 is closed, this is an open set. So this is intersection of two open sets. Okay, and intersection of a finite number of open sets is open. Okay, that's how the complement of this is open. Therefore, this set is closed. Therefore, F1 union F2 is closed. Okay, is closed, and therefore it belongs to F1 union F2 belongs to script F, because script F is collection of closure sets. And then you look at the you take this collection and go for the intersection. You have to check each of these sets F alphas, or each of these sets is a closure set. Okay, because each of these F alphas is a member here in script F. Script F is collection of closure sets. So each F alpha is closed. We have to show that their intersection is also closed. Okay, so let F alpha belongs to script F for alpha belongs to lambda. Means what? This means F alpha is closed. Okay, for each alpha. Okay, and we have to take their intersection. So if you consider intersection F alpha belongs to script lambda. We have to check whether this belongs to script lambda. Okay, so whether this belongs to script F. So means we have to check whether this is closed. To check something is closed, you look at its complement. Okay, if the complement of this set is open, then we can say this set is closed. Now let us look at the complement of this. What is the complement of this? It is union F alpha complement alpha belongs to script lambda. Okay, intersection of F alpha belongs to lambda complement is this becomes union, and complement comes here. F alpha complement it becomes, and each F alpha is in script F, and script F is collection of closure sets. So each F alpha is closed. Therefore, F alpha complement is open. So this is union. This is union of open sets. Union of open sets. Okay. whatever be the whatever be the size, whether it is countable or uncountable, any union of open sets is open. Any union of open sets is open. Therefore, this union is also open. Each F alpha complement is open because F alpha is closed. F alpha complement is open. Therefore, union of open sets is open. Okay. Therefore, complement of this set is open. Therefore, this set is closed. Okay. Therefore, intersection F alpha, alpha belongs to script lambda is closed. Okay, is closed. Is closed. Means it belongs to script F. Means it belongs to script F. Okay. Yeah. Right. That's how we can show that. You can show that if you are given a collection of closed sets, and then you can show that it is closed under finite unions. Means if you take finite number of entries from F, their union will also be a member in that, and it is closed under arbitrary intersections. Okay. If you take any collection of open sets, whether they're countable or uncountable, their intersection will again be a member in script F. Okay. Whenever script F is a collection of closed sets. This is opposite to the properties of a topology. In a topology, if F is a topology, then it is closed under arbitrary unions, and it is closed under finite intersections. Okay, right? And topology, a member of topology, any element of topology is called an open set. Any member of a topology is called an open set, and closed sets are the complements of open sets. Okay, so whatever holds for intersections, that for open sets, that holds for unions for closed sets, right? And this works for open sets. This is true with arbitrary union here. Therefore, for closed sets, this will be true for arbitrary intersections. So that is the change taking place when you deal with closed sets. Okay, and then I want to do this property. Right, SAQ3. Suppose script A is a collection of sets in X. Suppose script A is a collection of sets in X. Okay, satisfying the conditions. One, A belongs to script A, comma, B belongs to script A, implies, right? Implies A intersection B belongs to script A. Number two, A belongs to script A implies A complement belongs to script A. Okay. Prove that script A is an algebra. Script A is an algebra of sets. Okay. Suppose script A is a collection of sets in X such that the script A is closed under finite intersections. You take two elements from A and B, and then A intersection B will be a member in script A. And similarly, you take script A is closed under complements. You take capital A in script A complement will be in script A. Okay. Yeah. If script A has these properties, we have to show that script A is an algebra. Okay. What is an algebra? Algebra means it must have these properties. It must be closed under unions. Okay. A comma B belongs to script A, means A union B belongs to script A. Okay. This is one property for algebra. And the second property is, yeah, A belongs to script A implies a complement belongs to script A. Okay. Right. So, okay. A belongs to script A must imply a complement belongs to script A. So, for script A to be an algebra, it must be satisfying these two properties. Okay. Script A is an algebra, for now. These two properties are true. Okay. This property implies a complement belongs to script A. It is same as this. A belongs to script A implies a complement belongs to script A. This is complement. Sometimes, right, in our old books, this is a complement. Okay, this A tilde is also is written for complement of A. So we can as well use a complement. So a complement. Okay, these two are same. A second property and B is same. Let us prove this. Okay, let us prove this. So how can we prove? We want to use this. Okay, and using this, we want to obtain this. Okay, how can we obtain A union B? A union B. Can we write this in terms of intersections? Okay, so this is A complement, right? A complement intersection B complement whole complement, isn't it? What is complement of this by De Morgan's laws? Complement of A complement is A. The union becomes intersection becomes union, and then B complement is B. So A and B can be written as complement of this intersection. Okay, because complement of A complement is A, and intersection becomes union, and complement of B complement is B. So this is by De Morgan's law. Okay. Now if A and B are in A, A complement is also in A, and B complement is also in A. Right? Therefore, because of the second property, this is an element in script A, this is an element in script B, A. And script A is closed under finite intersections. Means if you take finite number of entries, the intersection will also be present in script A. Okay. So what can we say? A complement, B complement belongs to script A because A comma B belongs to script A by 1. Right? Capital B belong to script A. Therefore, A complement, B complement are members in script A by the second property. Okay, by 2. Okay, therefore these are members in this, and by first property, you can take the intersection of these two. A complement intersection B complement is again in script A by 1. What is 1? It is this. Script A is closed under finite intersections. If you take finite number of entries from script A, then intersection will again be a member in script A. Okay, this is assumption. So by the first assumption, you have that because there are elements in script A, their intersection will be present in script A by the first assumption. Okay, now you apply the second assumption on this. What is that? If a set is in script A, then its complement is present in script A. This implies that 2 implies that A complement intersection B complement is present in script A. Okay. If A is in script A complement is in script A. That is second assumption. So this is present in script A. Therefore, the complement of this is present in script A. What is this? This is equal to A. A complement is A. Union. This becomes union. This is B. B complement is B. Therefore, A and B is present in A. Therefore, A union B is present in A. Right? That's what ultimately we want. Okay. We started with A and B in script A. For them, we could show that A union B is in script A. Okay. So this we can obtain. This property we can obtain. We could show that script A is closed under union of finite number of sets. Okay, finite number of elements. And then the second property is same. Therefore, Therefore, script A becomes an algebra. Okay, we could prove the property A, and property B is same as property 1. Therefore, script, right? Property 2 is equal to A. These two properties are same. Therefore, script A is an algebra. Okay, that's how you can show that if a collection of sets is closed under finite intersections and complements, then it also becomes an algebra. Okay, it satisfies these two properties. And next is this one. Next is another SAQ. Yeah, this is SAQ4. SAQ4. If A is an algebra of sets in X, prove that if script A is an algebra, of sets in X, prove that A belongs to AI belongs to script A, I equal to 1 to n, implies A1 union A2 union dash 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 union AN belongs to script A. Okay, and A1 intersection A2 intersection and so on intersection AN belongs to script A. Okay, so we are given that script A is an algebra, and AI, capital AI, are elements from script A. Then we have to show that A is closed under arbitrary finite unions, A is closed under finite unions, and A is closed under finite intersections. This is what we have to show. Okay, how can we show? What is algebra? A is algebra. A is algebra means these two conditions are true. These two properties are true. A is an algebra. Script A is an algebra means these two conditions are true. It is closed under union of the two sets, and it is closed under arbitrary complements. Okay, so A is an algebra means if and only if A comma B belongs to script A implies A union B is in script A. Number 2. A belongs to script A implies A complement belongs to script A. Okay, script A is algebra means it is closed under finite unions, union of finite number of sets, and it is closed under complements. Okay, and from here we have to obtain this. How? Let n be any natural number. Here n is any natural number. We have to apply induction, mathematical induction, right? Case A, n equal to 2. If n is 2, you have A1, A2 belonging to A1, comma A2 belonging to script A, right? So if n is 2, you have A1, A2 belonging to script A, and this is, you take A1 in place of A and A2 in place of B, then A1 union A2 will be in script A. Okay, then this will be true. Okay, then because A is an algebra, since script A is an algebra, A1 union A2 will be in script A. Okay, union of any finite number of sets is union of two sets is again present in that, because script A is an algebra. Now assume this for n equal to k. Assume this for n equal to k. So let me give a number for this, right? Assume, let me call this 1. Okay, so let 1 be true for n equal to k. Will prove for n equal to k plus 1. Okay. Therefore, what this means, n equal to k means here you can take a1, a2 up to k, and their union is present in script a. Okay. So for yes, please.
Measure and integration topic, sir.
Yes.
Measure and integration, sir.
Oh, yes. These are preliminaries. I'm not teaching from the main portion. Okay. These are preliminaries. Did he teach you algebra? Did he speak about algebras?
Second year, sir, math. Second year, measure and integration topic.
Yes. This is measure integration only.
Okay.
Did talk about algebras?
No, sir.
No. You have to learn actually. He might have skipped.
Okay.
He might have skipped these points. So, so I thought you know them. Okay. You should be knowing. You should know sigma algebras, and then you should know first you should know algebras. Then you should know sigma algebras. Then you will be knowing Borel sets. Okay. To understand Borel sets, you need to know algebra, and then sigma algebra, and then Borel set. That is the sequence. Okay. So I'm discussing some properties of these algebras. So A1, yeah. Now I'm assuming this for n equal to k. So what means I'm taking A1, A2 up to AK. Then A1 union A2 up to AK will be in script A. Okay. So for A1, A2 up to AK belonging to A, their union A1 union A2 union and so on, union AK will be present in script A. This is assumption. We'll prove this for n equal to k plus 1. Okay. So consider AK plus 1 belonging to script A. Okay. And take this intersection. Consider A1 union A2 union and so on, union AK plus 1. Okay. Take the union of these k plus 1 sets, A1, A2, AK and AK plus 1. Take this union. This can be written as union of A1 union A1, A2 up to AK, union AK plus 1. Okay. This union of k plus 1 sets can be written as, you take the first k sets, A1, A2 up to AK, take their union as a single set, and then this set union AK plus 1. So this union of k plus 1 sets can be treated as union of two sets. This as one set and this as another set. Now, in place of A1 we can take this whole thing, and in place of A2 we can take this whole thing. So by this property, if A1, A2 are in script A, A1 union A2 is also in script A. By this property, if you call this some 3, right, or 2, yeah, if you call it 3, so 3 implies that, yeah. And by assumption, this is an element in script A by assumption. So, right, assumption implies A1 union A2 union AK is an element in script A. By assumption, this thing is A1 union A2 up to AK is in script A. That is hypothesis, right? That is assumption, induction assumption. Okay, so it is in script A. The first set is in script A, and this also is in script A. Okay, and we also so this belongs to script A. Further, AK plus 1 is also present in script A. This is assumption, right? AK plus 1 is present in script A. Now, this is a set in script A. This also is a set in script A. This is an element in script A. This also is an element in script A, and this is closed under union of two sets because of this property. Okay, 3. Now, 3 implies this thing. 3 implies A1 union A2 union dash 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 up to AK union AK plus 1 is equal to A1 union up to AK union AK plus 1, right? This is equal to this. I am rewriting this. And this is in script A. Okay? By this property, by this second property, by this property, because script A is algebra, it is closed under union of 2 sets. Okay, because of this property. In place of A1, I am taking this one, and in place of A2, I am taking this. Therefore, it is in script A. But so if you are taking K plus 1 sets, their intersection, their union is also member in A. Therefore, by mathematical induction, A1 union A2 union AN will be in script A for all AI belong to script A. Okay, right? So that's how you prove this. And what is the second property? It speaks about intersections. It speaks about intersections, and yeah. In this, in an algebra, A union B is an element in A, script A. Whenever A, B are elements in script A. From here, you get intersections. From here, you get intersections because you want intersection here, so you take union here. Okay, from this property you can obtain this property. Why? Because you want intersection here. Here you have to take union. If A is present in script A complement will be in script A, B complement will be in script A. Their union will be in script A, and its complement will be in script A. And complement with union here will be intersection. That's how you can show that A union for A and capital B in script A, intersection B is in script A. Okay, so yeah, so right, okay. Now, so let us write down that. So let A1, A2 belong to script A. I'll show that A1 intersection A2 is in script A. Okay, how? What is the complement of this? Yeah, you want A1 intersection A2. This can be written as A1 complement union A2 complement. By De Morgan's laws, this is complement of A1 complement is A1. Complement of A2 complement is A2. This union becomes intersection. Now, because script A is an algebra and A1 is in script A, A1 complement is in script A, A2 complement is also in script A. Therefore, these two are elements in script A, and script A is algebra. Therefore, their union is present in script A. So this is element in script A, and its complement is also present in script A. Let us write down. So A1, A2 belong to script A, implies A1 complement, A2 complement belongs to script A. Okay, and from here you will obtain that A1 complement union A2 complement is in script A, because script A is an algebra. Okay, their union will be present in script A. Why? This also is because script A is an algebra. Okay, if an element is present in script A, its complement is also present in script A, because script A is an algebra. Okay, now because it's an element in script A, its complement will also be present in script A. So this will be present in script A because script A is an algebra. Okay, this is because of this. Okay. This The reason for this is that script K is algebra. Okay, so if you are given two sets, you can show that their intersection is also present in script K. Now, again, as before, as we have done for union, you can proceed. What we did, we'll be assuming it for K. You will get A1 intersection A2 up to intersection AK will be present in script K, and you will try to obtain this for n equal to K plus 1. You will be considering AK plus 1. You will be going for the intersection of all these. And again, this intersection can be written as A1 intersection with unions replaced by intersections. This will be A1 intersection and so on intersection AK plus 1. This is, you treat this as one side, this as another side, and this is present right from the assumption. This will be in script K. This is also in script K, and now because of this, right, you will get that intersection of K sets will be present in script K. That's how you can obtain this property. Okay, the next one. It is similar to this. You replace unions by intersections. That is the only difference. Okay, so this is about algebra, and then yeah, you will be studying sigma algebra, and then you will be studying Borel sets. Okay, this I will continue later. Okay, just I want to discuss something with you. So without any preparation, I had to meet you. Okay, so I'd like to stop here. You want to ask something? Hello? Hello? Can I stop here?
Okay, sir.
Okay. I want see. Only in the morning I came to know about Ramalingaya that he is not taking class. Had he told me yesterday, I could have prepared some better. I did not prepare at all. Just to talk to you for some time, I discussed these points. Okay, right? So here I want to stop. Can I stop here?
Okay, sir.
Right. Thank you. Goodbye. Tomorrow Ramalingaya comes.
Okay, sir.
Bye.